Okay, so we have seen a bunch of techniques for second order differential equations. First we started with homogeneous differential equations. Linear ones are the simplest, and then using the general solution of the homogeneous differential equation, we saw how we can work out the answer for an inhomogeneous differential equation, provided we are able to find a particular solution for the inhomogeneous differential equation, right? So if you can find one particular solution, you just add it to the complementary function and you're done, right? Oftentimes it so happens that even finding one particular solution is not so easy, right? And so in this lecture we will look at a a general method for for finding out a particular solution for second order differential equations if you know the full general solution for the corresponding homogeneous differential equation, right? So this is inspired by a method which we have already seen, but with first order differential equations, right? And it's quite general in its applicability, and in fact it can be extended to even higher order differential equations. But today in this lecture we will look at second order differential equations alone. Okay, so let us recall what we did with first order differential equations. If somehow we were able to work out the homogeneous first order differential equation, which we have seen is always possible, right? So it's in fact you can write down the integrating factor and then you're done, right? So that's the advantage of a first order differential equation. So no matter how complicated p of x is, you will be able to at least formally write down this answer: y of x is equal to a times e to the minus integral p of x dx, right? It may or may not be possible to evaluate this integral in closed form, but this solution is always something you can write down formally. Now we saw how when you want to work out the solution for the inhomogeneous differential equation, it's first order, so there is only one free constant, so you elevate this constant to a function, right? So that's the educated guess which was suggested. So you start with this differential equation, and then you compute this quantity y of x is equal to a of x times e to the minus integral p of x dx, right? This part you just leave it as it is, but instead of just a constant a, you make it a function, and you implant this as an Onsorts into the differential equation with which you want to solve, namely the inhomogeneous differential equation, right? And now you have seen how this works out, right? You can go back and review this older lecture where we do this in great detail. So I mean, you just plug back in here, and then you can solve for if you force this to be a solution of this differential equation, and then it will give you a of x. A of x is given in terms of this integral dx q of x e to the integral p of x dx plus constant, and once you have a of x, you just multiply this with this exponential minus integral p of x dx, and you're done, right? So this is you have seen this same solution. Final solution is the same by other methods as well, but the key point to observe here and to build on is this method where you started with the homogeneous differential equation, worked out the solution, and then where you had this constant, free constant, if you make that into a function, and it was possible to use that as an Onsorts in a meaningful way to work out to get a particular solution for the inhomogeneous differential equation, right? And it turns out that this method generalizes even to higher order differential equations. So in particular we will look at second order differential equations in this discussion. So our goal is to start with a differential equation of this kind. So you have d squared y by dx squared plus p of x times dy by dx plus q of x times y is equal to some arbitrary function r of x, which lies on the right hand side, right, which we have seen is sometimes called the forcing term. Now the goal here is, if suppose by some means we know the full solution of this differential equation, right, which itself may not always be an easy problem, right? So because here we are looking at a scenario where both p of x and q of x may be arbitrary functions, right? So which by itself may turn out to be a hard problem, right? We have seen, of course, that if both p and q are constants, then we know how to solve it, right? So that is a solved problem. And but even for that scenario, if you make r of x to be extremely complicated, as of now we don't know of a systematic method to work out a particular solution, right? So which is, the point of this discussion is, if by some means, if we are able to get the full general solution, you need the full general solution of this homogeneous differential equation. It's not enough if you have some particular solution, right? If you have the full general solution of this homogeneous differential equation, so now of course there are going to be two of these, right? So there are two independent solutions. So you in general have a general solution which will have two free constants. So you will have something like y of x is equal to c1 y1 of x plus c2 y2 of x, where both y1 and y2 are solutions of this. So and they are linearly independent solutions which you can couple in this manner and write down the full general solution. So inspired by our first order differential equation and how this variation of parameter method works out, we elevate these coefficients c1 and c2 to the status of functions, right? So suppose we consider an Onsorts, we make this yp of x, a particular solution Onsorts, as nu1 of x or v1 of x times y1 plus v2 of x times y2 of x, where in place of these constants c1 and c2 we have some functions which are to be determined, right? So there is some freedom about these functions, but it doesn't matter which particular function you find. If you can find one particular function, we are done, right? So we have seen this in the past, that if you can by some means get any particular solution, you can just add the complementary function and then you're done. And complementary function is of course available here, which is the solution of this homogeneous differential equation. So now, making this the Onsorts, if you want to plug this into your original differential equation, you must find the derivative. So if you take a derivative of this function, you have dv1 by dx times y1 plus dv2 by dx times y2 plus v1 dy1 by dx plus v2 dy2 by dx. So there are all these terms which come in, 4 terms. Now, in order to simplify the algebra, and in fact it's an educated simplification, right? We know, because it works, it has been tested out by somebody and they have shown that if you make this assumption, it can yield for you a particular solution. So we make this assumption as well, right? Because we have the wisdom from hindsight. Somebody else has already done it and told us, right? So it's available in the textbooks, right? So the standard technique here is, so since we have this freedom, v1 and v2 are not so constrained that you don't have wiggle room. So in fact you can choose your v1 and v2 to be anything as long as yp is a particular function. So it turns out that if you make this assumption, you impose this condition, it's somewhat arbitrary, but its justification is that it will work out, as we will see, right? So you have to use some intuition to come up with a constraint of this kind. So we make this condition dv1 by dx times y1 plus dv2 by dx y2 equal to 0. If you put this condition, right, so what it does is it will greatly simplify the second derivative, right? So after all, we have to find the second derivative of this yp and then plug back into your original differential equation and make sure that it makes it all agrees. So in this case, if you make this assumption, these two terms will go, first two terms, and then so your dy p by dx is simply given by v1 times dy1 by dx plus v2 times dy2 by dx. So if you take another derivative, now you have dv1 by dx times dy1 by dx plus dv2 by dx dy2 by dx, plus then you have these terms involving the second order derivatives. right? So what this condition has ensured is that there are no second order derivatives in v1 and v2, right? So we want to work with just first order derivatives in these unknown functions. So that's what this condition does for us. As we will see in a moment, this is a simplification which allows us to in fact solve for v1 and v2. Okay, so if you so you have v1 of x times d squared y1 by dx squared plus v2 of x times d squared y2 of x by dx squared. Now we must use all these ingredients. So we have this long complicated expression, but not as long as it would have been if we had not made this assumption. Expression for the second derivative, then we have an expression for the first derivative, which is actually simpler than what I am showing here because the first two terms will be absent. So in fact it will have only just two terms, and then we have an expression for yp of x, which is of course the original Onsorts. If we use all of this information and plug back into this original differential equation, then in this exact manner, if we add all these three terms, it must add up to r of x. That's our condition, that's our requirement for yp. So that will give us differential equations in v1 and v2. So let's go back and plug these into the original inhomogeneous differential equation. So now we have this whole stuff is the second derivative of yp, d squared yp by dx squared. I have put down all these four terms, then plus p of x times the first derivative. The first derivative is just these guys, this part alone, because the first two terms add up to 0 according to the way our condition has been imposed. So I have p of x times v1 of x times dy1 by dx plus v2 of x times dy2 of x by dx, right? So it looks complicated, but it's really not very difficult. You just have to follow the algebra carefully. Plus q of x times the original expression for yp, right? So all I'm doing is plugging in my Onsorts with the conditions into this differential equation, and I have to make sure that it works out. So I have q of x times yp. Yp is v1 y1 plus v2 y2, and which is exactly what I have. Q times v1 y1 plus v2 y2. Now all of this must equal r of x. Now it is convenient to rearrange all this complicated stuff in this manner. So I put together dv1 by dx times dy1 by dx plus dv2 by dx times dy2 by dx. These are the first two terms. I just leave it as it is, put one bracket around them. Then I collect all terms which has a factor of this v1. So I have v1 of x times d squared y1 by dx squared plus p of x times dy1 by dx plus q of x times y1 of x. Each of these terms has a factor of v1 of x, which I pull out. And then there are these three terms which have factors of v2. Again, I find that this is v2 of x times d squared y2 of x by dx squared plus p of x dy2 of x by dx plus q of x times y2 of x, and that's it. I have exhausted all terms. I have just rearranged them in a nice, useful way, which is equal to r of x. Now, a moment's thought, if you look at this equation carefully, you see that in fact, this term and this term, the entire stuff in the brackets of the second term and the next stuff, this bracket term, both of these must vanish. This quantity and this quantity must vanish, because after all, what are y1 and y2? Y1 and y2 are solutions of the homogeneous differential equation, and this is the homogeneous differential equation. So we started with the assumption that y1 and y2 are solutions. They are independent solutions, but basically they are solutions of the homogeneous differential equation. Therefore, in fact, we have this great simplification which immediately follows. So now we have just two terms here. In fact, the left hand side with all these terms cancelling away, you just get dv1 by dx times dy1 by dx plus dv2 by dx dy2 by dx is equal to r of x. So now I have numbered this as equation 2, right? So let's go back and look at equation 1. So equation 1 is a condition we put in by hand. So I said dv1 by dx y1 plus dv2 by dx y2 equal to 0, and now you see there is if your v1 and v2 are arranged in such a way that yp is a particular solution of your original inhomogeneous differential equation, and this condition 1 holds. We have managed to show that even condition 2 holds, which is another linear equation. So we have two linear equations in two variables, and the two variables being dv1 by dx and dv2 by dx, because y1 and y2 are known functions, r is also a known function. So the only thing which is unknown is dv1 by dx and dv2 by dx. Of course, it's a 2 by 2 problem, linear equation problem. We know how to solve it, and the answer is simply dv1 of x by dx is equal to minus y2 times r of x divided by the Wronskian. So it turns out that this Wronskian appears because of this nice manner in which these derivatives come here. So you see, on the one hand here you have y1 and y2, but here the coefficients are the derivatives dy1 by dx and dy2 by dx. Therefore you get dv1 by dx is equal to minus y2 times r of x divided by w of y1 y2. So the Wronskian is the determinant of this function. So you will have y1 times dy2 by dx minus y2 times dy1 by dx, right? So this is something that you can verify. So dv1 by dx is equal to this expression, and then we also have dv2 by dx is equal to this expression y1 times r of x divided by the same Wronskian. Okay, so now these are linearly independent functions, so we are guaranteed that the Wronskian is not zero, right? So it's a useful observation to make. It's like a side remark, but it's important, right? So we have chosen these y1 and y2 to be independent, linearly independent solutions. Therefore we are guaranteed that their Wronskian is non-zero, and therefore these functions are going to be meaningful. So formally you can just integrate them, and then you have v1 of x is just the integral of this with respect to dx, and likewise v2 is the integral of this with respect to dx. So you will of course get some constant, right? So each of these integrals will give you some free constant, but in fact it doesn't matter for our purposes, because we are only interested in a particular solution. And the particular solution we started with the Onsorts yp of x is equal to v1 of x times y1 plus v2 of x times y2, and we have solved for this, at least formally. v1 is just integral minus y2 r of x divided by w dx, and v2 is integral y1 r of x divided by w of y1 comma y2 dx, right? So this is a final answer as far as the particular solution is concerned. Once we have the particular solution, of course we just add the complementary function, and then we have the full general solution for this problem, right? So formally it looks a little dense what we have done, but in fact it's just a clever and elegant way of working out a general solution for an inhomogeneous differential equation. If you know the general solution for the corresponding homogeneous equation, and at least formally you can write down one particular solution, and then you're done. So in fact this method is more general than what we have shown, and it can be carried through to even higher order differential equations, but that is something that we will allow you to play and try to figure this thing out on your own, or you can cook up your own differential equation and try to solve it using this method. So but let's look at an example of how this plays out in practice, drawn from a second order differential equation, which is actually very simple to write down. So you might think that this should have a very simple solution, but not unless you use the method that we have described here, right? So we know of course how to solve this. This is just like a harmonic oscillator problem, but where the external drive is a tan function. If it is a sine function or a cosine function, right, we know how to work with this. We also know exponentials, we have, or algebraic functions, so on, right? So if you have x squared, x to the power 4, whatever it is, we have given prescriptions for problems of this kind. So let's see what happens if you have tan of x. So the complementary solution is the familiar sine. So that is, you are solving for d squared y by dx squared plus y is equal to 0. That's the simplest differential equation, perhaps the first differential equation we have all, whose solution we are aware of from high school days, which is just C1 sine of x plus C2 cosine of x. So both the sine and the cosine will appear. Now to find a particular solution for this differential equation using the technique above, we will elevate these coefficients to the status of functions. So in place of C1 we'll put V1 of x, and in place of C2 we'll put V2 of x, and then implant this Onsorts yp as a particular solution into your original inhomogeneous differential equation. So differentiating, we have the first derivative is dv1 by dx times sine of x plus dv2 by dx times cosine of x plus v1 of x times cos x minus v2 of x times sine x, right? So now comes the choice that we make, right? Exactly like in the prescription, the general prescription which we gave. I mean, it's useful to work this out explicitly every time rather than try to memorize some solutions in terms of the Wronskian and all this. It's nice for a formal general prescription, but it is best to work it out explicitly every time you have a problem of this kind. So that's why I'm giving you an example and working it out in somewhat elaborate fashion. So we choose dv1 by dx times sine of x plus dv2 by dx times cosine of x to be 0, right? So that's the prescription which has been just handed down to us, and then we argue that it works, and therefore it's useful to adopt, right? We have seen that it works. So dv1 by dx sine of x plus dv2 by dx times cosine of x equal to 0. Thus dy c by dx is, we have a simplified expression, so it's simply v1 of x times cosine of x minus v2 of x times sine of x. So the first two terms add up to 0. So if we differentiate once again, so we have dv1 by dx cosine of x minus dv2 by x by dx times sine of x minus v1 of x times sine of x minus v2 of x times cosine of x. Now we have to plug all of this back into the original differential equation, which is actually a very simple differential equation. You have to just add the second derivative and the function itself, and it must give us tan of x, and the function is chosen to be this yp. So we take this this complicated looking stuff, but it's actually not so complicated, and in fact there will be simplification, as you will see. So you have all these 1, 2, 3, 4 terms. So first derivative times cosine of x minus dv2 by dx times sine of x minus v1 sine of x minus v2 of x cosine x plus, so this is where the simplification comes. When you add the function itself, it's v1 of x times sine of x plus v2 of x times cosine of x. So all these last 4 terms simply cancel, and then we must add these all up, whatever is remaining, which is just 2 terms, they must add up to give us tan of x. So the differential equation that we have, well, I mean, it's the second differential equation. We have dv1 by dx cosine of x minus dv2 by dx sine of x equal to tan x. So you can think of this equations 3 and 4 as coupled equations. So you have actually two first order equations. There are two unknowns, v1 and v2, and you have to solve for dv1 of x by dx and dv2 of x by dx separately. In fact, each of them will be separable, as we have seen, right? So it's not not coupled differential equations in their full complexity, but very straightforward. So in fact, you can write down dv1 by dx, immediately you can solve for this and you get sine of x, right? You can, if you wish, verify that the Wronskian is playing out and so on, but it's it's straightforward to directly solve for each of these unknowns. dv1 by dx is equal to sine of x, and dv2 by dx is minus sine squared of x divided by cos x. You can verify that indeed, if you plug this back in here, this times sine x times cosine x minus plus sine squared x by cos x, so which will just add up to tan x. So where you just have to make use of the fact that cosine squared plus sine x will give you 1, so sine x by cos x is equal to tan x. So it works out all right, the signs are all correct. So dv2 by dx is equal to cos squared x minus 1 by cos x. It's more convenient to write it this way. So cos squared x by cos x, it's cos x minus secant of x. So now the integrating the first equation is straightforward. So v1 of x is minus cos of x plus an arbitrary constant, but we are after a particular solution, so we don't care about the constant. We might as well just put it to 0. v1 of x is equal to minus cos x, and v2 of x, so the first term will give us a sine of x minus log of secant of x plus tan of x, right? So again there is an arbitrary constant which we just put it to be 0 because we don't worry about this constant here. We are after a particular solution, and the particular solution also is simplified now, you see. So I have yp is minus, so let's recall what we were after. So the Onsorts for the particular solution was v1 of x times sin x plus v2 of x times cosine of x. v1 of x is minus cos x, so minus cos x times sin x plus this whole stuff for v2 sin x minus log of secant of x plus tan x. The whole thing must be multiplied by cosine x. So now you see that there is going to be simplification. So cosine x minus cosine x minus sin x will cancel with sin x cosine x, and then we are just left with this one term which is minus cosine x log of secant x plus tan x, where our other compact simple expression for the particular solution after all the hard work. So we can in fact go ahead and write down the full general solution for this original differential equation, namely this rather simple looking, but as you have seen, which involves some careful analysis, this differential equation d squared y by dx squared plus y is equal to tan of x. The final answer is just the complementary solution c1 sin x plus c2 cos x minus cosine of x times log of secant x plus tan x, which is your particular solution, which we have just worked out using the method of variation of parameters. So you should play more with other kinds of functions you can put in place of tan x. You come up with something more complicated and see whether you may run into difficulties with integrating this, but in principle this method holds. And then if you can do it with second order differential equations, you can also try it out with maybe order 3 differential equations if you like, or do some small improvisations within this theme. It's a simple, elegant and beautiful method, and hopefully I managed to convince you on this. Thank you.